Okay, let's get started. So thank you for coming along to this. So this is joint work with a lot of people from several interlinked projects. I shall highlight some of them as we go through. So the foundations. People talk a lot about the foundations of computer science, and they usually mean this kind of thing. These are all motherhood and apple pie in this community. Discrete maths, logic, semantics, lambda calculus, type theory, all this good stuff. What we don't so often focus on is the actual foundations of computing as it is practiced. So, the transistors, the RTL, the processor architectures, the fine languages that people use of JavaScript and C++ and PHP and so on, network protocols and operating systems. And this is what the industry is really based on. And, it establishes, and the industry establishes these beautiful towers of construction with highly elegant user interfaces and, in some cases, very highly polished. But it is all above this stuff. It is not very much above this stuff. And indeed, it's very close all the time to falling over. We see this in the vast number of terrible security problems that people wrestle with. So, if you want to do something about this, how can you improve the foundations? How can you improve the foundations of a building which is already there, of a vast, elaborate and fragile building which is already there? So there is a process which some property owners sometimes have to go through, fortunately I never have, of underpinning. Underpinning is the process of strengthening the foundation of an existing building. And sometimes you need to do this because the original foundations aren't strong enough, or because the usage of the structure has changed, or because the underlying assumptions have changed. And all of these apply routinely to software systems, especially much of our software and much of our computational architecture was basically designed in the 60s and 70s when security was not a problem. So underpinning, classically it can be a very expensive process, but it is possible. So let's see how we can do that. So how can we establish trustworthy, not merely trusted, foundations for computing as it is normally practiced? And we'll focus here on how we can do this for the actual mainstream systems that everyone depends on for your telephones and laptops and what have you, not the clean ideal systems that we might as researchers prefer to have. And we'll be looking at this full scale and with all the complexities, so both fundamental complexities where things are really subtle for good reasons, and also the contingent complexities that have just arisen from historical accident and accumulation. And we aim to do this. A foundation is only a foundation if it's actually useful, right? So we aim to support better and more rigorous engineering of one kind or another. So sometimes that means full verification, but it also means using semantics in much more lightweight ways, but in this full-scale context. So if we're going to do any kind of verification work, at some point we have to make a shift from the physical reality of the real systems to the mathematical model that we're talking about. Right? And that has to be either just posited and taken out of thin air, which is frankly what we often do, or at best it has to be empirically validated. Right? We can do, at the end of the day, we can do no better than to experimentally test that our model is a reasonable model of reality. And given such a model, a well-validated model, in principle one might develop a fully verified stack above that, as people have tried to do for, well, many decades now and have succeeded in small, simple cases. Or in normal research practice, one might do some specific analysis or verification above this model. So in this talk, I'm going to be focusing on the architectural abstraction, right? ARM, x86, Power, and RISC-V, and that's where we'll make this shift from physical artifact to mathematics. But it's not forced, right? We could do this at many other levels, and indeed some of our group and many other groups have looked at some of these other things in their own terms. Not so much those at the bottom, they're a bit tricky. But the architectural abstraction is a very attractive place to do this from a verification point of view. So first, the hardware vendors do a tremendous amount of validation that hardware implements their architecture specs. Although one has to remember, this is not perfect. There still can be errata and defects. One never gets total certainty. And then it's relatively simple conceptually compared with high-level languages and operating systems and cloud infrastructure and what have you. And it's easier to get confidence that our verification actually relates to the thing which is running if we're ultimately verifying a binary which is running. So in this talk, there's a talk of two parts. So the first part I'll talk about production architecture as it is now, and I'll talk mostly about ARM, the A-class ARM that you see in mobile phones and tablets and so on, and new Apple laptops. We've also done work on RISC-V and IBM Power, but I'll just leave those aside mostly for now. And then in the second part of the talk, I'll talk about architecture perhaps as it should be, so the work of the CHERI project extending ARM and RISC-V and other architectures in ways to add hardware support for additional security protection. So, first part, production architecture as it is now. So here we're talking about the basic specification of the allowed behavior of processor hardware and the assumptions that software has to make above it, or can make above it. Right? And traditionally, this stuff gets published in books, quite large books like these ones. So the ARM manual now is 8,000 pages. And historically, these have not been terribly well defined, especially in the concurrency aspects. They've also historically been only prose and pseudocode, not mechanized in any way at all. And that means they've only been usable as documentation. They haven't provided oracles that you could use, executable oracles for testing or for analysis, or specifications for proof. So over the last decade or so, ARM have transitioned internally to a mechanized language for this pseudocode, and this was driven by Alistair Reid and others at ARM. And what we've done, in a way that we report in a Popple 2019 paper, is automatically translate that into a domain-specific language that we've developed, Sewell. For RISC-V, historically, also there was only text, in that case not even pseudocode, and there we've handwritten a Sewell specification, and that's now been adopted by RISC-V International, the new name of the RISC-V Foundation, as their official formal spec. So I said we had a domain-specific language, Sewell. So what is that? So it's an imperative first-order language. It's custom-built for ISA specification, not for general programming or general specification. And it's intentionally very simple. Right? It has very limited expressiveness, and that makes it relatively easy to analyze, which is good. And then a distinguishing fact about these ISA specifications is they tend to use a lot of bit vector operations, and actually some quite fancy dependent typing of those bit vector operations is necessary, so we have that. And then another interesting thing is that the behavior of register and memory actions here is not actually specified in the SAIL. That's left to an external memory model so that one can plug in some tool for relaxed memory concurrency. And it's open source, it's public. So from these SAIL specifications for ARM or RISC-V or other architectures, we can generate a whole bunch of different artifacts. Right? So here, the sort of SAIL ecosystem picture, we see a lot of different architecture specs at the top. From those we can generate sequential emulators in C, in some cases tests, theorem prover definitions for Koch and Isabelle and Whole 4, LaTeX documentation, and then both SMT versions and LEM versions that can be integrated with concurrency models. So let's focus in on the ARM model here. So based on the ARM internal model, the SAIL model for ARM v8a, this includes basically all the sequential behavior. So floating point and address translation and synchronous exceptions and the hypervisor mode and crypto instructions, all kinds of things. Right? And the world has not previously had such a complete and authoritative architecture description for any architecture. Right? So that model is available. It's about 100,000 lines of specification, so quite large compared with normal maths, but quite small compared to normal programs. And we'll see some of that in a few slides. Is it correct? Well, Alistair Reid, while he was still at ARM, tested a previous version of the SAIL model on the ARM internal architecture validation suite. It turns out to be pretty good. It also boots operating systems, so I think it is the first formal model that does that is complete enough to do that for production OSs. Is it usable for sequential testing? Yes, the emulator runs at a couple of hundred kips. Is it usable for proof? At least up to a point, yes. So Thomas Bauer-Rice has, for example, proved a characterization of address translation, and we'll talk more about proof later. So this is something that is available for you to use now, and we would love people to use it. Let me give you some idea of what it's like. So if we just focus in on one supposedly simple ARM instruction like this, add 1 to the value in the X3 register and put that in the X4 register. So this is one of the simplest instructions in ARM v8. And if you have a very specific goal in mind, say you're aiming to write a verified compiler, you might cheerfully make up the semantics of that, make up a partial semantics for that off the top of your head just by reading the manual. And it might look something like this. This is actually taken from one version of Concert. And this is not too complicated, right? You just see that you update the register state with some addition. If we look at the full form of this instruction in general, right, and then we look at its full specification, actually there's quite a lot going on. So we see here, so now I'm showing you the SAIL specification auto-translated from the ARM internal spec. So first you decode, you pattern match a bit vector of the instruction opcode that you fetched and pull out various fields. And then you decode some more, checking various cases, throwing an exception, not a processor exception, but a SAIL exception in some cases. And then, finally you start executing it and you compute, well, actually the pseudocode does both addition and subtraction, and you compute add with carry, and maybe you've negated one of the operands first, and then you compute some flags and so on. But then it's more complicated because you see here register accesses like this SP. Well, actually in ARM the stack pointer is a banked register, and what you get depends on the exception level. So there's a bunch of auxiliary functions that manage that. And then, well, finally you get to the actual arithmetic and the computation of the flags in terms of actually integer arithmetic, unbounded integer arithmetic in the ARM spec. Okay, so a few things to note about this. So there's a lot of detail there, but it's quite simple. Right? There's not much going on. well, sorry, there is a lot going on, but it's not conceptually difficult here. There's a lot of bit vector manipulation. We didn't see that much of it. Well, I didn't look closely enough to see it. I think I've said some of these things before. It's large, but not deep. So then, how do we make usable prover definitions out of this? Well, we translate, that's basically a first order imperative language, and we translate that with a monadic translation. And that dependent typing of vector lengths for the coq generation, we more or less retain that, and for Isabelle and whole 4, we monomorphize as much as is necessary. So in both Isabelle and whole 4, you can have a generic bit vector polymorphism, but not dependent types. So we monomorphize just enough to get down to that. And we aim to reduce, as far as we can, readable and usable code. So I'm not going to go into this in much detail, but just to give you a tiny snippet, here is the generated Isabelle from one of those functions that I just saw you. It's a little bit finicky, but not too bad. And the generated coq is basically the same kind of thing. These are all readable names that you see from the source. But that is a lot of complexity. So, and quite often, you don't need all of that complexity. So if you just look at that one instruction again, so we now have tooling produced by Alistair Armstrong called Isla, which is a symbolic evaluation tool. So it uses SMT solvers to simplify that full instruction semantics with respect to whatever constraints you might have on the opcodes or the architectural state. So for example, you might specialize that instruction knowing that you're exception level 2, and perhaps also knowing some specific alignment constraints on addresses or what have you. So if you run Isla on the binary you get by compiling that concrete instruction, then you get out a description in terms of SMT that really is essentially what you would like to have for that concrete instruction. Right? There's a register read, a register write, and a bit vector addition in between. Okay, so this is all the sequential behavior. So if we turn to concurrency, then we find things which are not so large, but quite subtle. And in this talk, I'm not really going to go into this, otherwise we would have to take another several hours, maybe 10. But in real architectures, especially ARM and RISC-V and Power, a lot of the hardware optimizations of out-of-order and speculative execution have some programmer visible effects. So one has to ask, what can programmers depend on? And we asked that question back in 2007, and then it was very, very unclear. Now, after a lot of work, partly by the people that I had on the front, and also by others, and by ARM and IBM and so on, we now have definitive, precise definitions of the allowed behavior of arbitrary user code. And these are in several styles: proved equivalent, you have axiomatic models, operational models, both operational in a microarchitectural style, which kind of follows the hardware intuition, and in this promising style, which is more abstract and a bit easier to work with, but less close to hardware. And Christopher Poulter and others have proved the equivalence of some of these models. So, okay, then you have a whole pile of stuff, and then you need tools to work with these. And previously, we've talked about RMM for these operational models, and Jean Glau and Luc Maranger have developed HERD for axiomatic models. What is new that I'd like to mention today is this Isla axiomatic tooling, again down to Alistair Armstrong, which integrates for the first time that full ISA specification of the sequential behavior with an axiomatic concurrency model. Right? So you can try that and use it. You get a web interface something like this. So you can type in litmus tests in the classical form, but these can now be really arbitrary ARM assembly language, well, at the end of the day, arbitrary ARM binaries, and you can feed in a pretty much arbitrary axiomatic model in a subset of the cat language, and it will compute what executions are allowed and what are not. Okay, that was user concurrency. I said that was now pretty well understood. When it comes to the interaction of concurrency and systems features of self-modifying code and cache maintenance and address translation and TLB maintenance, so this is still a work in progress. So we had a paper by Ben Simner and others at ESOP last year that looks at this first case, and work is going on both in our group and in ARM on these things. But Isla axiomatic also supports that, right? So now we can have litmus tests that involve self-modifying code and axiomatic models that cover this iCache and dcache maintenance and compute what behaviors are allowed and not. Okay, so now let me turn from architecture as it is to architecture as maybe it should be. So what are we faced with here? So we're faced with the problem that we know all too well, is that computers are terrible. They're really so terrible. They're atrocious. And we have all of these legacy design choices dating back to the 60s and 70s of systems languages that don't enforce protection and hardware that enforces protection only at a very coarse grain using virtual memory. And these are baked into the critical systems code base and really to the entire industry. So as PL people, we can try and come up with new languages and so on, and that's good and all. And things like Rust are certainly getting more traction, but it will be long, 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 long before anything replaces all of these. And none of those languages really gives strong guarantees for very low-level code. So the result of that, in the adversarial environment that we have today, that we didn't have in the 1970s, is that programming errors very often lead to exploitable vulnerabilities. And very many of these are due to some memory safety violation. 60% plus, according to recent statistics from Microsoft and Google. So if we look at this just concretely, if we take some piece of random C code, here's some C code that's got a global secret key and some code which is not supposed to be able to even access that secret key. And what does this code do? Well, it takes the address, well, first it creates those two globals, then it takes the address of X, and then it computes 1 plus the address of X. And, okay, that's allowed in C, and it might just so happen, depending on how these things are allocated, that 1 plus the address of X is the address of the secret key. And then if we try and access that secret key, well, if we actually do it with GCC, it'll print out the secret. Is that permitted in the C language? Well, sort of yes and no. So the ISO C standard says, more or less, that program has undefined behavior, and for any program with undefined behavior, the ISO standard doesn't constrain the behavior of implementations in any way. Right? That means it's the programmer's responsibility to avoid this kind of thing, and compilers can and do assume the absence of this kind of thing. Right? If we want to nail down exactly why this access is undefined behavior, then we need to somehow track the provenance of pointers. We need to know that when we try and dereference this, it was supposed to be a pointer to this object, or it originated as a pointer to this object, and it shouldn't be used to access any other object. And in other work that I'm not going to talk about today, this Cerberus Semantics by Memarian et al. Does this, and there's actually now a technical specification for ISO C in progress in the WG14C committee to make precise what that means. But making it precise doesn't make it go away. Right? So this just highlights the problem that we face. So CHERI is a project that's been running since about 2010, originated by Robert Watson, Simon Moore and Peter Neumann, and with myself and other semantics people joining a few years later. CHERI is a collection of ideas for architecture extensions to support hardware-enforced protection, both fine-grained memory protection that would rule out this kind of thing, and secure encapsulation. Right? It does so in a way that I'll explain in a bit more detail by adding unforgeable capabilities to these architectures. And it aims to do so in a way which is actually deployable with quite reasonable effort for existing systems. So let me just focus on this fine-grained memory protection for a second, and maybe we'll come back to the secure encapsulation a bit later. Yeah? So if we look at this program, if we run this in a normal implementation, the values of pointers are just machine words. If we look at this in CHERI-C, the value of pointers are capabilities. So on a 64-bit architecture, this would be a 128-bit compressed thing that encodes not just the address of the pointer, but also the base and the length and the permissions of the allocation that it's allowed to be used to access. And because you have these in your hand in the pointer value, the hardware can do a fast access time check that whatever you're trying to access is legal. So that means that, well, this thing will be undefined behavior in the semantics, or possibly an exploit in practice. Here, it will be guaranteed to trap. So there's a bunch of interesting design points here. I've mentioned some of them, so let's look at a few others. So the design, crucial here, is that the design of the ISA lets code shrink capabilities but never grow them. Right? And in addition to that 1 to 8 bits of address and base and bounds data, there's also a 1-bit tag. And that tag isn't normally addressable. You can't just write it. It's maintained by the hardware to prevent forging. So this distinguishes capabilities that have been legally constructed from anything else. And then there's a bunch of other aspects of the design which are crucial, but I'm not going to have time to talk about. That it's carefully designed to coexist nicely with existing C and C++ and ISAs, and to coexist nicely with existing virtual memory when you want to, and then with a bunch of machinery for sealed capabilities for secure encapsulation. I'm mostly not going to talk about today. The initial focus was on spatial memory safety, but then it also supports various approaches for temporal memory safety of one kind or another. So that comes at more cost, gives you more guarantee, still doesn't give you total guarantee. Okay, if we look at that, focus in on that fine-grained protection. So one might choose to use capabilities instead of integer pointers throughout some address space. Right? And in that world, you have an initial universal capability that's given to you by the hardware at power on, and then that gets successively chopped up into smaller pieces by the kernel and the linker and the compiler and the heap allocator and so on. And then one would be using that both for language level pointers, to stack and heap allocations and globals and so on, and also for pointers that occur in the implementation, pointers to stack pointers, return addresses, and so on. So if you have well-behaved C code, then you get all of this protection just by recompiling. And if you have C code which is pushing the limits of what's allowed, well, then you may need to adapt it a little bit. On the secure encapsulation side, so suppose you have some mutually untrusted bits of code, right, and you want to constrain interaction between them. So classic virtual memory works pretty okay for process granularity, but it doesn't scale all that well. Even if you have a gazillion browser tabs, that's pushing the boundaries of what you can do, and browsers don't always. So CHERI gives some mechanisms, again, which I can't really explain, to let you encapsulate chunks of untrusted code, and that might include chunks of untrusted code that were written without capabilities in mind, right? That are really just operating using normal pointers. Okay, back to the project. So this has been an academic project for the last 10 years or so across multiple DARPA programs with EPSRC funding, now with Innovate funding, donations from Google and DeepMind and so on. And it's very unusually, it's a project in which we've been able to do hardware and software and semantics co-design. So there's architecture design, initially of extensions to CHERI-MIPS and CHERI-RISC-V. There's hardware implementations. This is led by Simon Moore, using BlueSpec Verilog, running on FPGAs, extensions of QEMU to support it, and the software stack of adaptations of LLVM and linkers and FreeBSD and so on. And then on the semantic side, we've ensured that we've made it possible to make these architecture extensions be precisely defined, initially in a language called L3 by Anthony Fox, and more recently in Sewell. And that lets us do a variety of more rigorous engineering, both lightweight and heavyweight. So lightweight is a whole bunch of things which don't involve proof, but are absolutely essential and useful. Right? So this is using that formal ISA semantics as the design document. And the CHERI researchers and engineers have owned that over time. Using the semantics in the architecture specification means that the reference documentation is the same thing as the architecture spec. Making it executable as a test oracle, so auto-translating the architecture spec into C or OCaml or what have you, this is invaluable both for testing hardware against, as an oracle, and for software bring-up, as the architecture evolves. It lets us quickly explore design alternatives without re-implementing the hardware. It lets us do automatic test generation, especially with Brian Campbell and Ian Stark up in Edinburgh. And we've also auto-translated to SMT and used that to check some properties. So all of this fits in very well with the existing engineering practice of our colleagues. But then, we also want to get some honest guarantees at the end. Right? How do we know that these architectures do enforce the intended security protections? And indeed, how can we even state what those are? Right? So for this, we've used our Sewell infrastructure to generate theorem prover definitions that we can do machine-checked proof about. Right? And this is the kind of thing that we've proved. For any intra-domain trace, until you make a exception level crossing, let's say, the reachable capabilities from the final state are no greater than those of the initial state. Or for compartmentalization, any trace within a properly set up compartment cannot affect any other memory, and it can exit the compartment only in some controlled ways. So these are properties of arbitrary code above, in the first instance, the CHERI-MIPS ISA. And this is mechanised in Isabelle by Kinderland, Nienhuis and others in this security and privacy paper. We've also been able to adapt these proofs as the ISA evolved. Okay, so now let me skip ahead. So what about industrial CHERI? So this is a very large and very encouraging academic project. But can one argue that CHERI provides good protection at acceptable performance and software porting cost, sufficiently good that, ARM and Google and Apple and so on should just adopt it? So ARM and these other companies have been interested and involved for many years, but from the academic evaluation, it's actually really hard to know. Right? In order to definitively answer these questions, you have to evaluate it in a modern high-end superscalar core, not a small RISC-V or MIPS core. And you have to evaluate it on a large corpus of software. So to get industry to commit to an architectural change is, you will understand, a very big deal. But then it's hard to get industrial scale evidence until you've got an industrial scale demonstrator, and that's very expensive. So a few years ago, we saw an opportunity to ask the UK government for funding to do just this. And well, slightly to our surprise, it turned out. So for the last year or so, there's been running this 5-year Digital Security by Design programme. And this has about 70 million of UK government funding and 100+ million of industrial match funding. And it aims to create a version of the ARM architecture and an actual silicon processor and board and software and proofs to make it possible to evaluate whether this does work at scale in an industrial high-end processor design. This is the partners here are ARM, who are obviously doing the largest part of the work, and Cambridge, University of Edinburgh, Linaro, and then there's additional industry and academic R&D being funded. In this year, last year, ARM released for the first time an emulation model for this architecture, and next year, or possibly the year after, actual boards will be available. Not in great numbers, but they will be available. So Morello, then, this is a slide from ARM. This is an industrial demonstrator of a capability architecture. It's a prototype capability extension to the ARM architecture, so there's no guarantee that any of this will be incorporated into the mainline ARM architecture. And it's also a superset architecture, so it includes several features for experimentation. The board itself, well, the processor and the board, it's a quad-core high-end CPU. It's based on the Neoverse N1 core. It's got a GPU and a display controller and various other things. Right? So this is a very serious processor design. And then a processor on its own is no use. So then there are 2 software stacks being developed, both with a combination of work at Cambridge and in ARM. So the most well-developed one, I think it's fair to say, is an adaptation of BSD that can use capabilities everywhere and can have temporal memory protection turned on. And then there's also an adaptation of LLVM, various applications that have been ported, including WebKit and Python and all kinds of other stuff. So now, going back to the verification side, so the Morello ISA, it's being designed by ARM, with detailed discussion with the universities, extending this ARM v8a architecture that we saw before. So what we do is automatically translate that into a sales specification, and we've been able to do this from weekly drops of the ASL as it's been designed and improved. We use Sewell to generate Isabelle and SMT versions of that. We use SMT to check specific properties, for example, the compression scheme used. We use Isla to generate interesting sequences of tests, instruction sequence tests for hardware testing. And we use Isabelle for mechanised proof of generalized security properties of the kind that we were talking about before. And this has found not a huge number, but several security holes along the way. So pretty soon we expect to have machine-checked mathematical proofs of security properties of this full-scale industry architecture, and that has, I think, not previously been possible. Going back to transition, well, popping out a bit, sorry, how can CHERI be transitioned? So one path, and we certainly hope this will happen, although it's by no means guaranteed, is that the evaluation of Morello will be successful. This will be incorporated into the mainline ARM architecture. Google and Apple and Samsung and the other major ARM architecture partners will take it up, and it will be in your phone some years down the line everywhere. There are also other paths. So there's work, a lot of work on CHERI-RISC-V, and also a lot of work on the CHERI adaptation of the ARM microcontroller architecture, ARM-M. And there's an IP agreement that ensures that the basic ideas here are not tied to ARM. So one can perfectly well imagine CHERI x86 further in the future. Lots of exciting research also to be done above this on hardware and software and verification of all kinds. If you want more details for any of this as I come close to winding up, here's a bunch of links to the various papers. And then let me go back to the beginning. Right? So we talked about underpinning the foundations. Right? And so this is not really what most research focuses on, and in many contexts one isn't able to work at this scale. Right? But here I hope we've shown that it's possible, with some effort, to just push that tower just a little bit back towards the vertical. We have been able to affect major industrial practice by judicious application of semantics and verification in places where there clearly is, and industry knows there is a problem. And this is very satisfying to do, right? So this is not producing papers with one cute idea, but when one looks into what you have to do to make this work, all kinds of fascinating, serious technical problems pop out, like, for example, most of that relaxed memory stuff, or the dependent type system of Sewell, or some of the machinery that's being developed to make these proofs feasible, and so on. So computing is still a disaster, but maybe I leave you with some vestige of hope that possibly the tower can be underpinned with something slightly more trustworthy. And with that, I thank you for your attention, and I will be very happy to take questions.